This is eHobbyist blog, a log of electronics hobbyist activities aimed at city dwellers who have limited space, limited money, and limited time. My name is Neil. Welcome. In this video, I'm going to continue work on the power supply of the prototyping system. Having finished the rectification and filtering components, I'm now going to start work on external supplies. In particular, there is a variable positive supply going from 0 to 20 volts at 500 milliamps and a dual tracking supply going from minus 20 to 0 to plus 20 volts at 500 milliamps, where the negative tracks the positive supply. In both cases, we need a positive voltage regulator. And I came across this handwritten note. Title, Regulated Power Supply is adjustable from 0 to 38 volts. And then the name, Frank P. Miles, Rochester, New York, and a diagram showing 723 voltage regulator. And this is what interested me. I've worked with 723 regulators, used them in half a dozen different projects, and I've been through the spec sheets and so forth, and at no point did I see this regulator capable of going down to 0 volts. So this I found intriguing, particularly since I've had 2 or 3 723 chips laying around. The problem here is that I don't really know where these notes came from. That's disturbing because this thing appears to be just too good to be true. So I started up Google search. I'm first going to look for Frank P. Miles, the name appearing in my notes. I came across numerous hits, looked at some of them. Nothing really stood out as source of these notes. So instead of looking for Frank P. Miles, I looked for specifically the phrase I had in quotes, hoping to get some kind of hit. I'm really just trying to get some degree of confidence that these notes are valid and worthy of being pursued. And the Google search shows indeed there are a couple of hits. It's some Japanese database. Now, if you're looking for information on American electrical engineering, the last place you look for is an American website. And here it is. Here's an article, and it's exactly as quoted. The article comes from Electronics magazine in 1975. That's really cool. That's outstanding. My second search, slightly modified from the first, leads me to a PDF file. What's that PDF file here? Hey, could this be the article? Good grief, that's the article. I mean, that diagram is very close to what I drew. And this looks like the first page of a multi-paged article. I don't know how to get to the second page. But as far as I can see, the circuit diagram is the same. At least the first few formula are what is presented in this article. So this is the first page of a multi-page article. I don't know how to get to the subsequent pages, but this tells me that this article is in fact written and I have some degree of confidence in pursuing it. And so I will. Let me start off with 723 block and build in the input positive and negative lines using red and black with the colors. And let me just indicate that this is indeed VN, and in my case VN is about 29 volts. We're going to connect the input positive rail to V plus of the 723 chip and the negative to V minus. In the diagram, he's got the output Zener connected to ground. Let me just extend this negative. Now here is the compensation capacitor, 470 picofarads, and that gets connected from the compensation pin to the inverting input. And the compensation pin is essentially the output of the differential amplifier. Now let me draw R1, 18K resistor. That is connected to the non-inverting input and the voltage reference. According to my notes, R1 is chosen to minimize the loading on R3 and for stability and output swing. Here's the second resistor, R2, and now we've got a voltage divider dividing the Vref. That portion of Vref is connected to the non-inverting input. And we have a variable resistor, R3, that is connected across VREF and going to ground. And so some proportion of VREF is going to be available at the output of R3. And now R4 is going to be connected to the inverting amplifier, and that in turn is connected to the 5K resistor, which goes to the output. There's a 2N3055. 3055 is going to be the output power transistor for this voltage regulator. And let me show the connection, the emitter of the 3055 to the output. And let me just indicate that the 3055 is heat sinked. And we'll connect the base to the emitter through a 47 ohm leakage limiting resistor for the 3055. Now I'm adding Q2, a 2905 transistor, which is going to be connected to the base of Q1, the 3055. This is PNP and NPN, kind of a Zikli configuration, a complementary Darlington, I've heard it referred to as. And we want to connect the emitter of the 2905 to the input power, and we want to have a resistor between the base of Q1 and the collector current of the 723. That, according to the notes in this article, is there to limit the amount of current going through the 723 to no more than 10 milliamps. And now we have R9 on Vout, also connected to the positive input. And according to the notes of the article, this is there to make sure that the Zener regulation is maintained. Now we add Q3, which is going to be used as a switching transistor to implement the current limiting. The base is connected to the collector of the 3055. The collector of Q3 is connected to the base of Q2, so that when this thing is on, it's going to be moving current from the emitter of Q3 into the base of Q2, and that is effectively the way it's going to turn off Q2 and subsequently turn off Q1. So Q3 is used as a switching transistor to limit the current, and now all you need is something to establish the limiting voltage. If the voltage across R8 exceeds one diode drop, that's going to turn on Q3 and limit the current. Finally, we got a 100 microfarad output capacitor to prevent the regulator from oscillating by trying to follow small changes in the load, as might be experienced by a quick switching digital circuit. Various nodes of this are color-coded, and what I'm going to do with this is that when I go to breadboard it, I'm going to use the same colors so that I can look at a breadboard and refer back to the circuit diagram more easily for me. Bear in mind, I'm not a professional engineer. This sort of color coding makes the breadboarding more comprehensible. What I'm going to do is create a breadboard layout diagram, which will show how the components are going to be configured on the breadboard, and then go from that layout diagram to the breadboard itself. Start off here with a 723 and plug that into the middle. Connect the power. What I'm going to do is connect the output of the rectifier filter module to these binding posts and consequently the power distribution strips, and use this easy access to power regulators. The first row of the power distribution strip is the positive from the rectifier filter module, and I'm going to connect that to a vertical distribution strip. And then connect the negative to corresponding negative on the vertical distribution strip. So this red and black of power coming into the regulator. And we need to connect the positive from power input to the V plus of the 723. Connect the negative to V minus of the 723. Connect the negative to the output Zener, pin 9. Frequency compensation capacitor at 470 picos. And we'll connect that with colored leads that correspond to the colors in the circuit diagram. And now we have the frequency compensation capacitors in place. I'm using a color coding here to represent various sections and nodes on the circuit diagram. We have the capacitor hooked in. Now we're going to put in place some of these resistors. I'm indicating that a lot of these resistors are being mounted vertically, and that's just a mechanism for conserving space. I use the horizontal mounting of anything axial if I need to run traces under it. If I don't, I want to keep the square inches of PCB board or breadboard to a minimum. I want to see how compact I can get it, and so I'll mount axial components vertically. I don't have a breadboardable pot for 2.5K, so I'm putting an actual 2.5K pot in and connecting it as per the circuit diagram. I'll slap another resistor in, another resistor. Now I'm hooking in R4 and connecting that to the pot, R3, now R5. So we have the basic voltage dividers in place, and now I'm setting up Q1 3055 transistor. I've drawn it off to the right side. It'll be off the breadboard area. And now connect the output of the power transistor, the 3055, to a column of the vertical distribution strip. So adjacent vertical distribution strips, you have the input power, negative or ground, and then the output. The base of Q1 is now being connected to Q2 for my Zikli pair. And I have resistor R6, which is the base biasing resistor on Q1. Now connection of the output to R6. R9 in place, which is there to limit the output current but maintain Zener regulation. Now this is the current limiting resistor, R8. And finally, the output filter capacitor connected to the output voltage and to ground. Next step is to take this and breadboard it. In this video, I started work on the prototyping system's external power supply. I conducted some research around some old notes showing use of a 723 regulator IC in an adjustable power supply that went down to 0 volts. I created a color-coded circuit diagram based upon that research. And I created a color-coded breadboard layout corresponding to the circuit diagram. In the next video, we will be breadboarding and testing this circuit. If you like this video and the idea of the channel, click on the YouTube thumbs up icon. If you want to be notified as to when the next video is available, click on the YouTube subscribe button. If you want to suggest future directions or topics, make corrections to published videos, or voice your opinion on related matters, then leave a YouTube comment. If you want to see supplementary material that cannot be easily presented in video form, such as high-res graphics, files in different formats, lists of references, go to the corresponding website. Until the next time, good day.